I'm glad to see some familiar faces, and hope everyone's having a good time. And my talk today is on learning propositional logic with logic programming. So I'm interested in a bunch of different logics, and there are lots of logics out there, logic just being a formalization of rules of reasoning. So Boolean logic, predicate calculus, or predicate calculus first and second order with your universal and existential quantifiers, linear logics which model resource consumption, modal logics of possibility and necessity, temporal logics dealing with time and actually having a sense of index and when things happen when. Epistemic logic, logic of knowledge, modeling which agents know which things about a game, say, or what's common knowledge or what's just shared information. Computability logic, which I don't know almost anything about, but you should attend Fare's talk tomorrow afternoon. And then very simple logic, propositional logic, or in this case, I'll be calling it interchangeably sentential logic, because my reference is a very curious book, which I happened to find 2 copies of while I was roaming the halls of the math department at Indiana University, called Classical Sentential Logic Based on Logical Equivalence by Robert Katz, 1994. Haven't been able to find much of Mr. Katz, but he has a very good pamphlet. And I found it interesting because I wanted to learn more about how I would go about mechanizing deduction rules. And so I thought, start with very simple deduction rules, propositional logic, and while refreshing myself on what propositional logic is and how it operates and performing proofs by hand, I should also think about how I would make a machine do the same thing and teach a machine to do the same thing, in a sense. The conceit is we'll try to build up the computer from a neophyte, knowing nothing, to at least being able to represent and express propositional or sentential logic statements, to actually being able to prove or check the proofs of certain equivalences between propositional logic statements. So propositional logic or sentential logic. Proposition meaning, so propositions are statements which can have a truth value or can have a truth interpretation. Sentential meaning statements themselves. So you note that I had both Boolean and propositional or sentential logic, but it turns out that propositional logic is very similar, in fact maps directly to Boolean logic. So I presume everyone here is familiar with Boolean logic. Okay, very good. So your and, or, not, and, nor, implication, bidirectional implication, and of course only a couple of these are actually necessary. We could go entirely with nands and nors, but this one will build up from and, or, and not. And note that this is a classical logic, so we will allow ourselves double negation. I only have a couple of slides because I'd like to jump out into the REPL fairly shortly, but one of the interesting things about Katz's presentation of propositional logic is that it is based on syntactical rewrite rules. So when researching how other people had gone about writing theorem provers for propositional logic, because propositional logic is sound and complete, or has a sound and complete truth interpretation, you can compare 2 statements for equivalence by sweeping through all the possible values of their logic variables and comparing the truth interpretation, the semantic interpretation of the resulting statement with each other. So on the left-hand side here, you'll see a very simple truth table for A and B or C, and then the result of applying the distributivity rule, which results in A and B or A and C. And if you just go through and check all the possible values of A, B, and C, then you'll see that, and you can go through and check them, some of them. So B or C, that's going to be 0. In fact, all of these are going to be 0 or false. And it doesn't actually matter what you call it, as long as you have a consistent interpretation, because your A is 0 for the first half, true for the second half, and so anything and 0 or and false and bottom is going to yield 0. And over here, you just have enough zeros to keep them all false. And then our last 3 rows of this table return true, or 1. So we could build, and in fact, most of the propositional logic provers I found do build on top of this semantic shortcut, if you will. So we'll take our arbitrary inputs, our arbitrary antecedents, and we'll sweep through, and we'll take our consequent, and we'll reduce them into some sort of rigorous structure called a normal form, which is amenable to performing this kind of comparison, and then sweep through the values of all the logic variables, and perhaps if we're clever, we'll put it into a SAT solver, and then show that because we're getting the same set of truth interpretations, getting the same set of semantic interpretations, well, then both of these statements are equivalent. But this is somewhat unsatisfying because when we as humans do proofs, we usually have steps that we follow. We usually apply rules, and we can see a trace of those rules. And that's also how the pamphlet that I was following has a set of rewrite rules which preserve equivalence from left-hand side to right-hand side. And so instead of having to exhaustively check all the values of your logic variables, you can apply a rewrite rule which operates independent of the actual truth or falsity of any of the interior variables or any of the statements or substatements. So I care not for what A actually is, or for what the truth interpretation is of A, B, or C on the right-hand side, because by the rule of distributivity, if it is of the form A and B or C, then I can transform it into A and B or A and C. Okay. Can people in the front row see it? More or less? Okay, well, I will try to... well, this is why you should have GNOME terminal installed and not Xmonad. Okay. So, one of the advantages of, okay, so then this theorem prover, or the language I chose to accompany me as I was reading through this text, is miniKanren. And miniKanren is a Prolog-like language embedded or written as an embedded DSL inside of Scheme. And in this case, the advantage of miniKanren is that it's based off of it allows one to very closely match the presentation of the rules in Katz's book. So, for example, if I am concerned with statements, I will concern myself with any statement to begin with. But I want to know what any statement decomposes into. And any statement can be either a simple statement or a compound statement. Now, a simple statement is just a variable, or just a literal, something like the sky is red, or I have a banana, or something like that. And a compound statement is any statement which is connected together by one of the logical connectives, and or not. So if we have pardon me. If we have a compound statement, we can decompose it. There you go. If we have a compound statement, we can decompose it into its left and right-hand sides, and then we have a very simple grammar as to what any possible compound statement could be. And I've tried to make this huge according to my terminal font. So hopefully this is huge enough. If anyone would like to follow along on their own machines, you can go to, yes, github.com/jpt4/slp. All right, so compound statements, because we're only going to concern ourselves with the first three, and, or, and not, first three connectives, our grammar for our compound statements is quite simple and straightforward. Given any statement, any compound statement C, it could either be in the form of not, be in the form of and, or be in the form of O. And because this is a little bit of a miniKanren introduction as well, there's a kind of quirk where your relational statements, because miniKanren is a relational logic programming language, have O's at the end of them. So this lets us distinguish between the built-in scheme not and and O, not and and or. All right, so not or not O. If a compound statement is a simple statement, sorry, if a compound statement is any statement with a not connective prepending it, then I will recurse onto whatever is not the not connective. If our compound statement is and, in the form of and, defined down here, which is just a tuple of prepended by and, then our left-hand side, or our left component of our statement, and our right component of our statement, could also be any statement. And similarly for or. So we go quite directly from, once you talk about sentential logic, the logic of statements, to talking about any statement, which can either be simple or compound. And we only have three options for compound statements. And our only option for simple statements, or rather our many options for simple statements, are any literal which is not of the restricted literals, not, and or. So any symbol literal that is not equal to, not, and, or. What kind of experience does this crowd have with Prolog and or Prolog-likes or miniKanren likes? Right. 1, 2, whoever has seen Prolog before, raise their hand. Okay, cool. So if you've seen Prolog, then the twist and the refinement of miniKanren is that it doesn't allow any of the imperative operations of Prolog. So it is purely relational, strictly relational, and anything that you run forwards, you should be able to run backwards. Any holes you have in your input or your output should, in theory, be filled by the term search that runs in the background of miniKanren. And our cond here is just pattern matching, or condi is just pattern matching. And you can think of this almost directly like an or statement. So any statement is, or an or clause, any statement is either a simple statement or a compound statement. And the cool thing is that this pretty much follows directly from, it is rather transparent in reading through a textbook on propositional logic, and you see, I can build up statements, or I can build propositions from my literals, and I can build them up with connectives, and then if I want to prove things about them, I just need to decompose them back into, or be able to decompose them back into their primitive forms. And so, let's actually do that. All right, so let's see what our nascent theorem prover thinks a simple statement is. Okay. So it could be anything. This is an indexed variable, indexed logic variable. It can be anything that is not and or not, so long as that anything is a symbol, which we'll find exactly matches the pattern match that we have for simple statement.
It's still touching. So if you could maybe shift the screen the way the text is on the right side.
Okay, I can do that.
Yeah, rather than a horizontal split, it's vertical split. Yeah, this works.
Thank you.
Now the slides are pretty bad.
All right, we'll run that again. So, and if we attempt to query for more possibilities of what our nascent system thinks a simple statement is, we'll find, if we ask it for every possible answer that it thinks it could return for what a simple statement is, we'll find that it just thinks that a simple statement exactly follows the grammar, which we had defined right here. Okay, so compound statement. What does our pupil think a compound statement is? Oh, okay, so a compound statement could be a not statement. And now we get into the interesting parts of logic programming. So it could be a not statement, or it could be a not of a not statement. Why? Because we can recurse inside of the not. And it could be an and statement. And all of this you might think of as boilerplate, telling us that yes, we have two index logic variables and they can only have certain values. In this case, they can be symbols, and both of them are precluded from being any of the reserved symbols. It can be an or statement. Okay, so let's see if we get anything more complex, because we did define a recursive grammar. And 100 of them. All right, so any statement, or any compound statement, could include the and of a variable, and of a, or a and, not and bc, not or, not a, not b, and any other combination allowable by our grammar, and only those allowable by our grammar. So we can also test to see whether or not it will accept, or how it will answer, if we try to pass it a malformed statement. So compound statement, the literal of A, returns false, or rather returns no result. There is no possible assignment to P which will satisfy compound statement being the literal of A. But a simple statement should be just fine. All right, so it looks as if we can in fact write a program that we can query and will return grammatical propositional logic statements. And we can get more complicated with this. We could say something like I don't know, not it is raining. And that's a valid compound statement. Which also may just be a valid any statement. So here's one of the first twists to keep in mind, that when you encounter things which are proved for any statement, they can include both simple and compound statements. But if for whatever reason you encounter strictly a compound statement, that means that you're precluded from dealing with the proposition directly, dealing with the simple literal of whatever it is, of whatever content you could substitute for your logic variable A, B, C, or what have you. All right, so So let's keep on going. Oh, frozen again. Pardon me. All right. So, like I said, when I was investigating how other kinds of theorem provers determine the equivalency of two statements in propositional logic, they will do so normally by producing by proving a semantic equivalence, and then jump from the syntactic or jump from the original statement of your antecedent, move to a semantic interpretation, prove that semantic interpretation as being equivalent to the consequent that you're trying to derive. So since they're not bound by keeping things in a human-readable format, but they don't have to produce a proof trace, and they can perform arbitrary manipulation internally on the structure of your antecedent and consequent, they will often employ what are called normal forms. And normal form is a way of regularizing any given propositional logic statement into a common pattern, into a common grammar. The two commonly encountered normal forms are conjunctive normal form, where you produce an and of or statements. You produce a single conjunct of possibly multiple disjunctive statements. Or disjunctive normal form, which is the dual of that, where you produce a single or of multiple and statements. Now, just as a side, since this is done by so many other theorem provers, it might be interesting to see if we can do it too in miniKanren. And indeed we can. The algorithm for this comes from a presentation from the Academia Sinica, so I wasn't able to find any other source that actually provided an algorithm that you could take an arbitrary, that gave as clear a breakdown of how to take an arbitrary propositional logic statement and convert it into conjunctive or disjunctive normal forms. So we'll also see that this algorithm lends itself very nicely to expression in relational logic, logic programming language. All right. So let's take an arbitrary statement. I don't know, not A, or let's try not and A, B, not and or A, B. And let's actually put the or outside. So we're going to try to reduce our propositional logic statement into conjunctive normal form. So we won't make it too easy on our machine and put the conjunct outside. We'll put the disjunct outside. And let's make these here we go. Okay, so our statement is the inverse, not of the disjunct of the conjunct of A and B, and the conjunct of C and D. And we want to see if we can first of all, we want to check to see if this is in conjunctive normal form to begin with. Because if, if it is, then our task should be complete. And it is not. So CNFL, but how do we know that it's not? Well, we have a grammar for what conjunctive normal form looks like. Which in this case and this grammar is, I should note, top-down and monotone and context-free. So whenever we are parsing our statement to determine whether or not it is in fact in conjunctive normal form, we don't have to worry about capturing variables across scopes. So as long as we correctly scope our input statement, we don't have to worry about there being any kind of unhygienic shadowing or capturing of variables between elements of our statement. So we take in our original statement that we want to know if it's in conjunctive normal form, and we ask ourselves, is it just already on its own just a disjunction of simple statements that can't be broken down any further? In which case, well then yes, it's in conjunctive normal form. And if it isn't in just a simple, in this case, a simple disjunct, then it has to be the case that it begins with that its outermost connective is an and, is a conjunction, and then the two internal ones, or rather, sorry, the leftmost one should be in a simple disjunction, and then the right one should be in conjunctive normal form. So we take our statement and we look at each piece in turn and see, okay, is it a simple disjunction that we can't decompose any further? And then, all right, well, if it is, then we'll examine the rest of it. Or is it just a simple disjunction that doesn't need to be decomposed any further? In which case we're finished. But just checking to see, just verifying to see whether or not our statement is in conjunctive normal form isn't particularly interesting. We'd like to coerce a statement not in conjunctive normal form into one. Which, let's see, which in order to do, we've got to pass through a couple of steps. So for this case, we'll extend our connectives just a little bit to demonstrate the full algorithm. We'll extend our connectives to also include the implication connective, which you can think of as if then, if P then Q, and this is not terribly much more or artificial than our ands, ors, and nots, because our ands, ors, and nots could of course be combined together to form nans and nors, and we would only need a single connective, and our implication, our if P then Q, is of course not P or Q. So if we have a sentence, if we have a statement, for whatever reason, that not A implies B. Because again, we're unconcerned with what A and B actually are. These could be arbitrary propositions, arbitrary statements. We're concerned only with the form, only with the relation between our literal statements and the connectives, which build them up into more and more complicated statements about the world. So, we can have such a statement that not A implies B. And the first thing we're going to do on our way to a conjunctive normal form is remove the implications So it's definitely not the case that this statement has no implications, because, and if we didn't know that ourselves, we could inquire and find that yes, indeed, this is not, or rather it fails, our program has failed to determine, or has failed to find a satisfying value of q that would allow for imply free to be true. And since it can't find one, then one doesn't exist. It could be the case that, well, if it were to run forever, and so we don't always, if we do have a finite negation, then we can be quite confident that our query is in fact incorrect, but a query could be correct, or it could be a query could be correct, but given that this is given that miniKanren is capable of encoding Turing-complete programs, if we were to ask something very complicated of it, it could spin forever. But usually, it just gives us a result straight out. Okay, so we know that this statement is not free of implications. And not only do we know this statement, but now our program, our slightly more intelligent theorem, or proto-theorem prover, knows that this statement is not free of implications. Let's see what an implication-free form would look like. Makes sense. It's going to be the disjunct of the not of the first. So, not A, along with B. Well, the next stage of getting to normal form, of conjunctive normal form, is to bring it into negation normal form. And our negation normal form is a way of removing any double negations. So double negations you can eliminate for free in a classical logic. So not A is equivalent to A. This is distinct from our intuitionistic logics or some other non-classical logics in which knowing the not of A and knowing A and knowing the not of A are three separate statements about the world. But since this is all classical, we're allowed to eliminate double negations. And we want to eliminate double negations so we can keep on drilling down, keep on moving in closer and closer until we can determine, or until we can actually grasp our primitive simple statements themselves. So, what does a double negation-free statement look like? Well, it could just be a variable, it could just be a literal variable, a simple statement outright. Or it could be a statement that only has a single connective, only has a single negation connective prepending it. Or it could be a conjunct or a disjunct, both of which themselves, the left and right hand side of our conjuncts or disjuncts, are in negation normal form. So again, this is a context-free grammar. We're just monotonically burrowing in, recursing down until we hit our base case. Again, confirm, yes. The next stage of our transformation is indeed not in negation normal form, but we can make it so that it is and lo and behold, it burrows down, finds that we have a not of A, and eliminates it. Eliminates the double negation prepending A. All right, so now we actually have a fairly So since we take a look now at our, since we can take a look at the result of running our negation normal form procedure on top of the previous result of applying our implication-free procedure, now we can ask, well, is or of AB in conjunctive normal form? And we will find, in fact, that it is, because our grammar for conjunctive normal forms doesn't disallow all disjuncts entirely, it just disallows top-level disjuncts, disallows top-level or statements. It allows them, it disallows them if there's anything if they're top level and there's anything in any conjuncts inside that could be promoted to being higher and higher level. And we'll show we get the same thing out. So what we get in the end is or AB, and although it is the case that or AB is equivalent to not A implies B. The process by which we went about this requires us to keep manual track of all of our rules. We don't have a nice proof trace out here saying, okay, we've made this transform, this transform, this transform, this transform. We have to do it all by hand. So a proper theorem prover should allow us to keep track, to actually produce a trace of or keep track for us of what steps it takes to transform one statement into another. And the particular set of transforms, particular set of equivalence rules, that I followed when building this are here defined in basically pseudo-notation. We've got our double negation, as we saw in the conjunctive normal form example, where if you have not of x, then you can yield an x. Idempotency, so you can have, if you have and of x and x, well then you can just get rid of, you can eliminate the and eliminate one of the x's and return only your x, return only your, if you have two statements that are identical and you're conjuncting them together, then it is equivalent to have only having the statement itself. It is not always the case that you can assume that a connective works the same way when you have your left and right substatements switched. So we have to specify that we do specifically have commutativity. And also we have a grouping rules, and the grouping rules for and allow associativity. And for all of these, we'll see that we not only have these basic rules, but we also have their symmetries, duals, and symmetric duals pretty much for free. So by a symmetry, we basically mean applying commutativity at the level of equivalence. So if I have idempotency and xx yields x, well then I should be able to have symmetric idempotency where seeing x, I can introduce the conjunct of x and x. And so on and so forth for the rest of them. And if I have idempotency, I should be able to have the dual of idempotency, which, let me refresh myself on what yes, so wherever I have ands, I should be able to introduce ors and retain the same, and then also retain a valid transformation. And then your symmetric dual is going to be the composition of your dual and symmetric variants on top of your basic rule. So when we as humans are applying deduction rules, rules of logic, if we have something like, okay, idempotency, but I also know that I can do idempotency with and xx yielding x, or if I see a single x and I need to, for whatever reason, introduce a conjunct, introduce an and, say I'm going to apply later down the line, I don't know, distributivity or De Morgan's rule, and I need to have a conjunct so I can do that. It doesn't strike us as, or at least didn't strike me, as being something I had to be quite so explicit about. I would just say, they're all of a single class of possible rules I could apply. But when you're instructing a machine where you're trying to build up a program that begins by knowing nothing about how to manipulate logical forms, then you must be extremely precise. And the base rules are not enough. You also have to be able to generate the all the entries, all the elements of your families of rules. So your symmetrics, your duals, and your symmetric duals. So in this case, our end result of generating all such things is a lot of rules. Right. We have, so for all of our 8 basic rules, we also have a total of 24 because we have our total of 32 because we have our basic rules, and then we have their symmetric equivalent, their dual, and their symmetric dual. And right here, they're all expressed as in a pseudocode. But the nice thing about having miniKanren built into Scheme is that we can use Scheme's metaprogramming and its list manipulation to generate the code which captures, or rather which generates from our pseudocode, from our notation for what double negation looks like in a slightly more human readable form into the actual machine variant of what double negation looks like. So if we've got double negation over here, pretty directly obvious, is fairly directly interpretable as the name, the left-hand side, and the right-hand side. That gets converted into a procedure, our miniKanren procedure, which we can, which captures which defines the computer's understanding of what double negation is. And we can, and I will note that there is nowhere in here define double negation or define dual of double negation or sim of double negation. So we only leverage Scheme's metaprogramming to generate all of our actual rules, all the source code of the procedures that miniKanren actually executes, and which we have accessible to us at the REPL here. Yes. So let's see. All right. So let's see this actually prove something. With a trace. Oh, okay. Yes. So let's first take a look at what rules are introduced into in Chapter 1, which are just the rules you already saw. Double negation, idempotency, commutativity, associativity, absorption, distributivity, De Morgan's, and dichotomy. And then we'll see what kind of prover, or what the source code of theorem prover actually looks like when generated on the basis of these rules. And we've got all of our rule clauses down here, all of our special rule clauses down here, and then some boilerplate above well, not quite boilerplate, but with some common elements above, which just break down our statements, our potentially compound statements, into their component not, ands, and ors. So we'll note that nowhere in here are we going through the conjunctive normal form, truth table semantics. We are operating directly on top of the statements themselves, and decomposing them into, or decomposing any compound statement into their components, whether they're connected via not, and, or, and that we're able to do this because propositional logic is in fact a context-free grammar. All right. So let's actually, now one thing, if anyone's done anything with, everyone who's done things with Prolog knows that you've got to have your cuts in the right place so that it'll actually run fast. And so we'll do a simple, well, we'll inquire of our prover something simple so that we'll get a result back in a decent amount of time. Let's say something like okay. We'll try it first just to see if it can actually address a rule correctly, which I'm certain it can. Rather, if we query it and we pass it something which we know is just a pattern match on a rule, will it be able to correctly pattern match on that rule, which it yeah. Aha, okay. So, somewhere in our proof search, we have in fact found multiple possible things that we can derive that are true from and not A of not A. Now, some of them are rather trivial, like and of not A and not A is in fact equivalent to itself. Well, that's nice to know that we have checked that edge case. And if we recurse down into the subtrees, into the not A and the not A of the conjunct, well, those two things could be equivalent to themselves as well. All right, well, let's go to check that edge case. But eventually we find that if you have and of not A and not A, that we can in fact apply the idempotency rule and yield not A in the end. And this does not just tell us that and of not A, not A is equivalent to not A, but it also gives us the reason why and tells us when the proof is over. So let's see if we make it slightly more difficult. And as we increase the possible applications of rules that our theorem prover could apply, we increase the possible to humans trivial edge cases or human trivial cases where there's no reason for any of us to go searching down all of these other pathways. And then our goal is to build the machine up to the point where it can in fact not only give us the correct answer, but also give us the correct answer in a reasonably performant and human consistent way. Which we may have confounded it in the time we have allotted. We let it run for a long time. Aha, and here we are. that we can go down a subtrace, recurring onto both sides, our left-hand and right-hand side of our conjunct, and we'll negate or encounter double negation of A, and we'll eliminate those double negations here. And then we'll end up with and of not of A and A. And since now we're on the right track, let's keep on looking. And here we are. A proper and A of A, which then would yield A right there. Cool. So it looks like our 997th possible proof in fact includes a trace which yields us in the end A, which is what you wanted in the beginning, because and of not A, apply double negation twice, apply idempotency, and there we have it. So this theorem prover was very interesting as a learning aid, because all of these edge cases, all of the rabbit holes one can go down when trying to exhaustively prove something in a very simple-minded brute force fashion are not the kinds of things which humans actually do when we create our own proofs. And the process of trying to confine, of building up a program that was both expressive enough to accurately generate and verify that statements which I knew were equivalent were in fact equivalent, but yet not so expressive, not so free-ranging that it yields, or that it takes 1,000 proof searches to find a 3-step proof. Gave me a great appreciation for the immense power that humans are wielding, even when we're in 0th order, very simple propositional logic. There are lots of better theorem provers, so like they're rather both better in multiple senses. They're more expressive, that are more performant. You can use, if you applied types to this, as opposed to just having term rewrites of untyped literals, then you can get lots of nice speed-ups. You can go to full dependent typing with Cock and Agden, Idris, and so on and so forth. But as far as a learning tool, working through, or always having to check to see, not only could I understand the material itself, but could I impart a degree of understanding to something that was not me, was a useful reflection, a useful mirror on my understanding of the topic. And I'll take 1 or 2 questions now, since I don't see the next speaker. And I thank you very much. Yes, question?
Does this have a way to disallow absurdity?
Pardon?
Does it have a way to disallow absurdity, so A and not A?
Ah, yes. So with A and not A, we can check it. Yes, so the question was, is there a way to disallow absurdity or to disallow contradictory statements? So A and not A, I actually probably ran that a while back. So there are certain ways in which A and not A are valid, as in it is, if you don't recur any further, any deeper into it, then the statement itself remains a statement, and it remains a grammatical statement. And it looks like all it's going to do is keep on recurring into and saying, yes, all of the component statements are in fact statements. So no, this one doesn't apply that interpretation of absurdity. That seems like it's almost a semantic interpretation, although you could encode that as a syntax rule. But yes, at this point, it's not reducing it any further. So you could consider that to be not acknowledging the absurdity by entering into an infinite loop. All right. So again, you'll see me running around for the next day or two. I'll be happy to answer any questions you might have about miniKanren or logic programming in general. And I thank you all very much. And you can check this out on my GitHub. And I hope the next speaker has a good talk. Thank you.